Summer, 1967. A Morrison-Knudsen D9G operator on the East Keyway cut at Dworshak watches his single shank ripper track across exposed granite, and the line it draws is 4 feet longer than every adjacent pass. He shuts down immediately. That 4 feet of extra track is either a scratch or a structural weakness plane in the foundation of a 717-foot dam. 3.5 million acre-feet will push against this wall. The Corps needs to know which one it is. The Army Corps geologist is already crossing the canyon floor. He has the foliation survey in his head and knows the dip angle at this elevation by outer memory. What he finds on that rock face in the next 10 minutes stops the machine or clears it. The question at Dworshak in 1967 is not whether the rock is hard. It is. The question is whether the D9G has opened a plane that will eventually move under 6.6 million cubic yards of concrete. Every decision made on this foundation is permanent. Let me tell you about the North Fork Clearwater River before there was a dam, because you need to understand what Congress authorized in 1962 to understand what the machines were actually dealing with 4 years later in that canyon. The Clearwater Basin, floods. The 1948 flood, the 1964 flood, the downstream valley absorbed the water and the losses every time. The Corps proposed one structure to control the entire watershed, a dam tall enough to hold back whatever the basin could deliver. Congress authorized it in 1962. The site survey placed the dam at the North Fork Canyon near Orofino, 4 miles northwest, narrow walls, granite, gneiss, bedrock. Solid from the surface, the foundation had to be verified from below, which meant excavating to solid rock. That excavation was the entire job. By 1965, the canyon rim was active, access roads being cut, staging areas cleared, equipment positioning. The D8H and D9G fleet came in behind the road builders. Their assignment: remove every cubic foot of overburden and weathered rock from the foundation zone down to solid granite. The D8H ran the canyon wall keyway cuts. 69,400 pounds operating weight, 270 flywheel horsepower, single shank ripper on the rear. On near vertical granite wall faces, 270 horsepower is not comfortable. It is exactly what the job requires and no more than that. The D9G ran the heavy keyway passes, 90,850 pounds operating weight, 385 flywheel horsepower. At full tractive effort, a D9G ripper tooth drives 40,000 to 60,000 pounds through its tip into the rock, in massive granite that fractures cleanly. In foliated gneiss, so it does something else. Dworshak's bedrock is granite gneiss. Granite recrystallized under extreme pressure into alternating mineral bands called foliation. The bonding between those bands is weaker than the crystal bonding within them. A ripper tooth finds that structural difference whether the operator intends it to or not. In early 1966, a 40-foot diameter diversion tunnel redirected the North Fork around the dam site, and a 110-foot cofferdam held the river back. The canyon floor was exposed for the first time. The D8 and D9 fleet moved down into it and the keyway excavation began. Before we get into the specifics, if this is the kind of content you've been looking for, consider subscribing. Everything on this channel is built around real machines, real operators, and real jobs. No manufacturer talking points, no content written by someone who has never been on a job site. If that matters to you, the subscribe button is how you tell us. And leave a comment. If you've run a single shank ripper in hard rock, what did it feel like when the tooth followed a seam instead of cutting through it? What did the machine tell you before anyone else on that site knew? Now, back to Dworshak. The keyway excavation required cutting slots into the canyon walls at design depths, the structural tie between concrete and rock that transfers the dam's full horizontal load into the foundation. This is where the surface survey's geological picture diverged from what the machines found below. The foliation at Dworshak dips toward the river. Some weakness planes running parallel to the canyon walls and angling toward the water. This is a dam foundation geologist's worst-case orientation. Potential sliding surfaces aligned in the direction of the horizontal load the dam will apply to the foundation. When a D9G ripper tooth follows a foliation plane instead of cutting across it, the resistance drops and the machine advances past the intended stop. The operator feels it before he can see it, the track running longer than adjacent passes. The machine moving too easily through what should be solid rock. The Corps established a field protocol for the entire excavation phase. Any ripper track running longer or smoother than adjacent passes required a halt and on-site geological assessment before the machine continued. Every D8 and D9 on the keyway excavation operated under this rule. Production stopped when the rock required it. The mechanical evolution of bulldozers, history's most punishing projects, and the technical details no one else covers, that's what lives in the membership section. Join, and you get full access to 20-plus minute deep dives built for people like you. Now, see back to Dworshak. The first confirmed foliation plane incident came during the 1967 east wall keyway cuts. A D9G operator noticed the ripper running long. Resistance dropped, and the machine advanced past the established cut line. The track extended 4 anomalous feet beyond the surrounding pattern. Machine shut down. Geologists called to the floor. The Army Corps geologist examined the exposed face within the hour. The ripper track matched the foliation dip angle to within 2 degrees. This was not a random scratch in the granite. The tooth had followed a structural weakness, planed directly into the foundation zone of the dam. The confirmed foliation track triggered the grouting protocol. Drill into the open plane, inject pressurized cement grout until the plane closes, hydraulic test the result, then return the D9G to work in that section. Discover, halt, treat, verify, then proceed. That sequence would repeat hundreds of times in this canyon. Grout injection into the Dworshak foliation planes ran at 50 to 150 pounds per square inch, varying with depth and geometry. The Corps used Lugen testing, a hydraulic permeability measurement, to verify plane closure before concrete placement was authorized over each treated section. The grouting program expanded as excavation exposed more of the foundation. What the initial survey characterized as isolated foliation zones turned out to be continuous planes running across the full canyon wall. The program scaled accordingly. The construction schedule moved with it for the second time. Think about what this canyon looked like during the foundation phase. Ripper machines working the walls below. Geologists assessing each pass. Drill crews grouting confirmed planes, and 700 feet above, at the canyon rim, D8 operators were running a completely different operation, one with no room to make a mistake twice. Blast debris from the keyway excavation had to be cleared from the canyon rim. The Army Corps photograph documents it directly. 2 D8 bulldozers working the tunnel portal area, pushing material from the rim over the edge. 700 feet of open air begins at the blade's discharge point. This is not standard canyon edge procedure. The operator's manual addresses slope angles and blade extension parameters. It does not address 700 feet of open air at the blade discharge point. The operators who ran that canyon rim knew exactly where the manual ended and the actual job began. A D8H pushing a loaded blade over a canyon rim shifts its center of gravity toward the front idler. If edge material gives way at the moment of full blade load, the machine follows the material over the edge. The margin between controlled work and the point of no return is measured in feet, not yards. No machines went over the rim during the Dworshak excavation. 2 years. Thousands of pushes to the edge. The safety record reflects operational discipline that doesn't appear in any formal project document. It appears in the machine count at the end, which matched the machine count at the start. By mid-1967, the foundation excavation had a rhythm. D9G machines ripping keyway slots, Corps geologists assessing each pass, drill crews treating confirmed planes, D8 machines on the rim. The canyon was becoming a certified dam foundation, one ripper pass at a time, deliberately and without shortcuts. The competing force at Dworshak was not a single event. It was cumulative geology. Every new keyway slot exposed more foliation structure. Every new structure required a decision. By late 1967, the grouting program had expanded to a scale that required the construction schedule to be revised for the second time. The Corps documented every foliation plane incident during the foundation phase: location, depth, dip angle, track length, grout volume injected, post-treatment Lugen test result. By the end of the 1966 to 1968 excavation, that dataset covered the entire canyon wall foundation zone in mapped, measured detail. Here's what the Corps was managing by late 1967. A foundation treatment program expanded beyond original scope, a schedule under pressure, and a D8/D9 fleet still pushing keyway excavation toward a completion date that had already moved twice and might move again. The decision structure never changed under schedule pressure: assess, treat, verify, proceed. What changed was the scale. The Corps ultimately injected grout into hundreds of individual foliation planes across the canyon walls before the foundation was accepted for concrete placement. The schedule absorbed it. The foundation required it. Foundation acceptance required Army Corps geological sign-off on every keyway section before concrete forms could be set. A geologist walking the exposed surface, examining ripper marks, cross-referencing grouting records, and accepting or rejecting each zone. Not paperwork. Physical verification in the rock itself. If this story meant something to you, maybe buy me a coffee while I build the next one. Hit the thanks button below. It's a small gesture, but it tells me this reached you. Let's continue with Dworshak. By 1968, the foundation excavation phase was complete. Granite gneiss exposed across the full foundation footprint, canyon floor, both walls, keyway slots cut and treated. The geological record of what the machines had found and how the Corps had responded was documented, filed, and complete. The Dworshak Foundation treatment produced the most comprehensive granite gneiss dam foundation dataset in Corps of Engineers history. Foliation mapping, ripper plane correlation, grouting records, filed with the Walla Walla District, available to every subsequent Corps dam project in the Pacific Northwest that followed. First concrete pours began in 1968 as foundation sections cleared one by one. A cableway spanning the 1,400-foot canyon width carried 12 cubic yard buckets from the rim batch plant down to the forming crews below. The dam started rising from the foundation the D8S and D9S had certified. 6.6 million cubic yards of concrete. Hoover Dam used 3.25 million. Dworshak is straight gravity, not an arch. Every pound of hydrostatic load transfers directly into the grouted granite gneiss foundation that the D8 and D9 fleet spent 2 years preparing and certifying, cableway running 6 days a week, forming crews on 2 shifts, concrete poured in horizontal lifts toward the final crest elevation. The 717-foot measurement is from streambed to crest. The D9G keyway slots from 1966 are at the bottom of all 6.6 million cubic yards above them. The D8 and D9 fleet did something easy to overlook at this project's scale. They qualified the foundation. Every cubic yard of concrete poured after 1968 rests on rock that was examined and treated because of what the ripper teeth found. Worked in those canyon walls in 1966 and 1967. The machines that ran the Dworshak keyway excavation were Morrison-Knudsen fleet units, contractors' iron on a fixed-term job. When the foundation phase ended, they moved to the next project. The canyon walls they scored and shaped remained, covered by concrete before the first generator turned. Construction of Dworshak Dam was completed in summer 1973. The first generating unit came online that year. Second and third units followed. The reservoir filled 3.5 million acre-feet of water behind 717 feet of concrete in a canyon that was a wild river 8 years earlier. 717 feet, the tallest straight-axis concrete dam in the Western Hemisphere. Not a curved arch distributing load laterally, not a buttressed gravity structure. A straight wall of concrete held by mass, geometry, and the foundation the D8 and D9 fleet certified during 1966 and 1967. Third tallest dam in the United States overall, centered behind Oroville and Hoover, both of which benefit from arch or arch gravity load transfer geometry. Dworshak has none of that. Every pound of hydrostatic pressure from 3.5 million acre-feet goes directly into that grouted gneiss foundation. Dworshak is still operating. The reservoir extends 53 miles up the North Fork Clearwater. All three units produce approximately 400 megawatts at full output. One of the world's largest steelhead hatcheries operates at the base of the dam, or in the canyon the D8 and D9 fleet opened up. The 1966 to 1968 foundation dataset informed core foundation treatment at subsequent Pacific Northwest Dam projects. The foliation mapping protocol and grouting procedures developed at Dworshak became the standard approach for metamorphic rock dam foundations in the Walla Walla district, written into the practice because the machines made it necessary. What the D8 and D9 operators at Dworshak established was a methodology, running rippers in real-time coordination with geological assessment, or treating machine behavior as geological data. That was not standard practice in 1966. The work in that canyon made it standard for every hard rock dam foundation that followed. The North Fork Clearwater still runs below Dworshak's base. The canyon walls above the reservoir line still carry ripper scoring from the 1966 to 1968 excavation where the waterline hasn't covered them. The work is still visible. It has been holding 3.5 million acre-feet behind 717 feet of concrete since 1973. If this is the kind of heavy equipment content you want to keep watching, subscribe to the channel. More machines. Well, more jobs, more operators who actually knew what they were doing. And if you ran iron like this, or worked on it, sold it, bought it at auction, or inherited it from someone who did, tell us in the comments. What machine? What job? How many hours? What you do differently with what you know now. The people who ran this equipment are the reason anyone cares about it. We want to hear from them.